We've got a lot of stuff to cover today. Get your clickers ready. We're going to do some clicking in just a minute. We have exam 1 coming up Tuesday. And we're going to review a couple more parts of the study procedure and the exam taking procedures. Let me just draw your attention to the SI schedule up here. Right here, you have a SI Monday at 9 in Classroom Building 1, Room 109, 9 till 9:50. And then you have the SI review, which goes 3:30 to 5 o'clock, but it's in, I think it's Nicholson 108 instead of 111. So I highly recommend those, especially for last minute review and stuff to get ready for exam 1. Desiree. No, one of them is well, I don't know, but they're probably, but the review is the one at 3:30, and it goes till 5. So go to both if you can. If you can't, you can't. All right. We're going to have some homework over the weekend, and by the way, I have some verbal instruction for you concerning homework, Chapter 2 mini review inside the Great Rivers website. And there's a discussion thread about it. Dr. B, how come I can only take one attempt? And, because students would show me, somebody put up a screen grab. I don't know if the student is here, but, I can take, my account works differently because I'm an administrator and the author, so I don't have a student account, I have an administrator account. So it doesn't work the same way your guys's does. But I found the secret. Somebody from first hour. Has anybody figured out how to do more than one attempt on that? You did? Good. Anybody else? What's the secret? What? It does? When did you take it? Wait a minute. No, not web courses. Yeah, okay. Okay, sorry to fake you out there. No, I'm talking about in the textbook website. You really juked me on that one. The textbook website, Great Rivers Learning, you take the test and then it says that's your attempt. But the secret of getting to the additional attempts is to go back into the chapter and scamper down to the very bottom of it again, and then it will let you try the exam again. And the student that told me that this morning had taken 2 attempts. So I don't know how it works after you've done 7 attempts. But do that. So you have to go the long way to get back to taking another attempt. All right. And in addition, there's like a little, I don't know if you noticed it, but there's like a little teeny menu pull down at the top of the chapter, and the pull down takes you to the quiz. But it's like really tiny. And I don't know if that'll work. But anyways, go back into the chapter, down the bottom to the end of chapter 2, down by the footnotes, and then you'll be good. You take it again. A few more comments getting you ready for exam 1. Exam procedures. We went over this, some exam procedures. I'll reinforce them today. What I want to reinforce is be on time. And the more on time you can be, the more time you're going to have to take it. I budget for 60 minutes, and we have an hour and 20 minutes. So hopefully it won't take you guys 20 minutes to get organized. Now the seating is going to be slightly different. We're going to put you in very specific rows, very specific number of people in each row. Like usually the front row we keep clear for people to come in late. Okay. Then we keep the very back clear, except for people that need to use the desks and stuff. But we'll have you in very specific rows and stuff like that. And that will take some time, but hopefully not 20 minutes. So whatever we don't need for that, and then we pass out the tests, and then you guys will, so hopefully it'll be like 64 minutes or even more. You know, and the more prompt that you can be, the more time you'll get for that. And I also want to emphasize for being prompt and on time and not tardy. If you come after the first person has finished the test and left the room, you may not take the test. This will be your dropped exam. And then you're under the gun for exam 2 and 3. You got to make it. All right? So to avoid being in that squeeze, I mean, it's no skin off your nose. You know, if you are late, you know, stuff happens. I understand that. But if you are, to that extent, late, then you may not take the test, and that'll be your dropped exam. But then you can just crush exam 2 and exam 3, and you're good. You know. Don't forget, this is the first of 3 midterms, and we keep the best 2. If you're here for all 3, hopefully you'll have 2 good ones and 1 that's not so good. All right? But if you're only here for 2 of them, then we take whatever you got. If one of them is a stinky one, that's, you know, tough toenails. But most of you will be here for all 3, so that's the main part. Now, a few of you will be over in SAS and taking the test there. Just instead of coming here to the lecture, I'll just report to SAS. And hopefully you know the procedure over there. You'll be doing the Scantron as usual, and they'll collect that from you. But then the clicking items, you won't be using your clickers because you're going to be way over there, and the clickers don't, you know, reach that far. So what you're going to do is just write the clicker items on paper, on the test itself, you know, like there'll be some open space for you, and circle your answer. And then what I'll do is I'll go in and grade it by hand, the old-fashioned way, using a red ink pen, all right? Kind of a throwback to the old days. So that'll work good. It's, you know, so you're good. You're squared away. Just report over there, and they'll take care of you. Everything's squared away. Okay. Again, no cell phone for any reason, and we'll be watching. So just, you know, bring your calculator, and you won't have to worry about your cell phone. We had some harsh penalties for students that were caught cheating over the summer. Bring iClicker and your Scantron, and it's the raspberry colored one with the Pegasus logo. So go to the SGA office. Don't show up without it. Don't let everybody know that you're a total newbie. Coming to the test without a Scantron. And, you know, we'll get it to you. You know, somebody will have an extra one, but you don't want to stand out like that. Just bring one. You'll be good. Pencil and eraser, calculator, and the iClicker as well. And there'll be scratch work area on the test. You'll be able to write on the test. You'll put your name on the test, and you'll hand it back in. You'll put your name and PID on the Scantron. Bring your ID card. Have that with you because that's got your ID number on it. And you'll hand in the Scantron, and then you'll cut on out of here. So that's good. All right. Now I have to pause the YouTube clicker on. If you haven't used your clicker in the past, it's frequency DD, so press and hold the power button down for 2 seconds. The rectangle in the upper left will flash. It'll blink, and then press in D, and then D again, and you'll get the Go Nitro message, and you'll be on the session. You'll be able to click. Don't click yet. You don't even have the question. So here's your first question. talk to me after lecture. Okay, clicker question number 1 for today. Coverage of the exam. Sadora, we'll get you squared away. Don't worry. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Yeah, this is the coverage. So as much, and I'll give you a rundown at the end of lecture today of exactly where in chapter 3 we're going to stop. Okay, so let's talk about chapter 3 now. Newton's laws of motion. And keep your clicker handy because we got a ton of clicking to do. Now, we talked about Newton's first law. It's Galileo's law of inertia. Basically, here's one way to write it. Every object retains its state of rest or its state of uniform straight line motion, constant velocity in other words, unless acted upon by an unbalanced force. So an example of that, just think of an apple in an apple tree. It's up there, just kind of sitting on the limb, and it's got a stem that attaches it to the branch. But in reality, there's forces that are balanced. There's the upward pull force of the stem. Stem is made of a fibrous, so it can achieve some upward pull from the branch to the apple. And then, of course, gravity is acting downward, and so that's the opposite direction. And they balance. All right, so they're balanced. And its state of motion, in this case, remains at rest. All right? And we talked about other situations where the forces balance and it's in a state of motion. All right? And that's kosher as well. Now, if the stem weakens, they'll eventually dry out in the fall. So this time of year, if you're out in like Washington State or up in Vermont, looking at apples in the apple orchard, the stem is going to dry out. It's going to weaken. The balance will fail. The stem won't be able to, you're still going to have the same amount of weight force pulling down because gravity never fails, never stops. But the stem might weaken, and then bang, it's going to fall down and conk you on the head like Sir Isaac Newton. And the day that he discovered the law of universal gravitation, supposedly. All right, so that's one example to kind of tell you about, okay, balanced forces, yeah, state of rest, good. Everything balances. State of rest stays the state of rest until the forces don't balance, and then you get something that changes. Now, another way to look at it, the state of motion. If you're in a I discussed this in chapter 3. If you're on the UCF shuttle bus and you're in motion, down a straightaway on a smooth road at constant speed, which is kind of rare here at UCF, but theoretically they could drive it on a straightaway that's level and at a constant speed, like 25 miles per hour. For a few seconds, and you're out in the aisle, you just go, you don't have to hold on to anything, because you're in motion with the bus. But as soon as and everything is bolted down to the bus is going to stay with the bus. You're not bolted down. You're on your feet. You're on the aisle. So if the bus changes its state of motion, you will not. And so if he speeds up to 26 miles an hour straight ahead, then like in the upper picture here, oops, wrong. You're going to lurch backwards. And you don't even have to think about it. Your stomach, your sense of balance knows this part of the first law. If you're in this mythical shuttle bus, 25 miles per hour, constant speed, constant direction, it's on the straightaway, and there's no bumps in the road or anything, if he turns to the right, you're going to lurch to the left. So you're going to bump your left hip into the seat next to you on the left. All right? Because you're going to want to keep going straight. The bus is cutting over to the right. And that's fine. Everything that's with the bus bolted down is going to cut to the right as well. But not you. Unless you do what you normally do. You hold on for dear life. All right? You're in the shuttle. I see somebody up here in one of the middle rows. They went, yeah. You're riding on those shuttle buses, and I understand that sometimes the shuttle from the apartment complexes out on Alafaya, they hit more than one apartment complex, and some of the ones, the last on the way into UCF, the last apartment complex, you can't get on. The bus is already full. So I know they get crowded. And so you're out there in the aisle and you got to stabilize fore and aft, port and starboard, and that's normal. And you don't even think about it because the bus is going to be going. It's not going to be perfectly level. It's not going to be smooth, and it's not going to be constant velocity. In fact, sometimes those guys drive like maniacs in the shuttle buses. At least that's what I think. So this is another way to think of the first law. Law of inertia. The bus goes one way. If you're not bolted down with the bus, you're just on your feet, you're going to leave your feet because your feet aren't bolted down either unless you stabilize. And that stabilization is like bolting yourself down. Your vice-like grip. Now, another third thing about the first law of motion, another example. Galileo said if you're looking at the motion of an object and there's no forces in that direction, then you're not going to get any acceleration in that direction. So, for instance, if you don't have any gravity that acts horizontally, then your x component of the motion is just going to be like, constant velocity, whatever you have. All right, and here's a good example of it. So separating the up and down from the left and right. Look at this diagram. It's a quarterback throwing a football to a wide receiver, and it looks like a mighty throw, even though the picture's only about 3 yards away. But anyways, if you look at the vertical arrows, the upward light blue arrows, see if I see these light blue arrows? Now look at them. They're changing in length. This first one, in the first image of the football, that's got a big upward arrow. But the next one, it still has an upward arrow, but it's not as long. That's because on its way up, it loses upward speed. All right? There's no such thing as horizontal gravity, so the horizontal arrows here, they're always to the right, and they're always the same size. Now, over here on the other side of the parabola, you start getting bigger arrows because now you're on the downhill. Now you're on the back side of the parabola, and your delta V is now you're on your way down, so you're getting more downward speed. And so over here, Giovanni, you got your biggest arrow of the 5. All right, and it's downward. This downward arrow and this upward arrow are the big ones. All right. How much vertical speed is there right here at the very top? 0. That defines the top. Go ahead and make a note of that. The top of the arc, the fancy word for that is apogee, A-P-O-G-E-E, which is like a NASA term for the point on the orbit around the Earth that's furthest away from the Earth. Apo means away. G, G-E-E, G-E-E for Earth, geo. And on an orbit around the Earth, they're slightly elliptical, so there'll be a point where it's furthest away from the Earth. And then the other point of the orbit is called perigee. Let me spell that one for you. Perigee. Now, we don't have to worry about perigee. Para means above or next to the Earth, and so that's the point closest to the Earth. But this one at the top of the arc, that's the apogee. It's the point on the parabola that's furthest away from the center of the Earth. It's furthest away from the ground, and therefore furthest away from the center of the Earth. Okay, so up there at apogee, v is equal to 0. That defines apogee. So you can always figure the exact height of apogee if you know the initial upward speed. So if I tell you, go ahead and make a note of this. It's not in the notes, but I'll verbally add this. If I tell you that the initial upward speed is 9.8 meters per second, that means it's going to take 1 second of upward motion to lose all of it. So you have 1 second to apogee. If I tell you that if you start with 19.6 upward speed, that means in 1 second you'll lose half of it, and in 2 seconds you'll have lost all of it, and so apogee is 2 seconds away. And you know what else that means? From apogee back down to the ground is 2 seconds. And that means a total hang time, if it were a baseball or a football, a total hang time of about 4 seconds, which is about what they do up in the NFL. A good punt, about 4 seconds of hang time. All right? See, so there's a lot to this. So this whole idea, there's no such thing as horizontal gravity. All right, here's the horizontal equation of motion. There's no free fall in that one. It's just a distance rectangle. Now, x as a function of time, x of t, is equal to x at time t equals 0, or x of 0. And, that's this term here, first term on the right. And then plus my speed times time. So my initial Vix of times time, that's my distance rectangle. So this is saying whatever I started with, and then whatever the distance rectangle gives me. And that'll be my final x of t, my final position, x at time t. And hey, you guys, Vix doesn't change. Why is there no delta V? Because there's no such thing as horizontal gravity. All right, so now Galileo said, yeah, go ahead, separate this one out. It's convenient. That's a horizontal, that's left and right. So left and right, everything is easy as taking a walk through the park. Now, vertically, yeah, you still got to deal with gravity. So here's the one, this is problem 12, I think, from homework 3. By the way, I extended homework 3, so now it's due Tuesday next week at 10:30, I think, and another few attempts. So some students were asking for a little more extra practice time, so you got it. If you already crushed it, you're good. But if you want to do it again a couple times with your study group, good. You got a few extra attempts. And by the way, students, that is why I give you more than one attempt on the homework. I give you usually a minimum of 4. Sometimes I'll give you a few more for practice with your study group, with your study partner, or SI, or whatever you choose to do. So this one, this one is, y is a function of time, y of t, is equal to, all right, your initial position in the y-axis, vertical graph, part of the graph paper. So whatever you start with. And then if you start with some upward motion, like a football or shooting a basketball, over the hand of your defender and over to the net, you got to give it a little bit of upward. Okay, it's not a slam dunk. It's just, you got to arc it over. So you have a little bit of VIY, and therefore you have some VIY times t, distance rectangle, but you also have a distance rectangle here, 1/2 gt squared, and in this one, g must be used as 9.8 negative 9.8 meters per second squared. Because here you're talking about a position, not a distance. So, if you're just chucking stuff off the roof of the library, hey, did you see that news report about the hurricane? And that the guys at NOAA, they were looking at the radar data and they saw an 83-foot wave in the radar. From space, they can actually measure, the waves and stuff. And that's like the UCF library. Can you imagine? You're out there. Whew, that's a big wave. Anybody here surf? You ever take a 10-foot wave? Yeah. Supposedly we're going to have 10-foot surf out here from this storm. Anyway, so you separate the equations of motion. This is the accelerated part, horizontal, no horizontal gravity. You don't have just distance rectangle. This is distance rectangle plus a distance triangle, plus your initial y coordinate. And as I mentioned in the textbook, this one can all be these two equations. You can show that they're equivalent to a y equals x squared type parabola that you see in Algebra 2 trig class or geometry class or calculus class up here at UCF. And that equation, go ahead and jot it down in your notes, y equals 1/2 x squared, or y equals x squared, or y equals ax squared. Y equals something times x squared. That's always a parabola, second, x to the second power. And that's always a parabola. It could be, a dish-shaped parabola or a bump-shaped upside-down parabola. At the end of chapter 2, I mentioned how to do that these two equations, this one and this one, can be combined into a parabola. And what we did in the first hour, we did a short talking PDF up here on the dot cam. And I'll set it up for you guys to look at it too. We're going to try to save a little bit of time. It'll be up in the Talking PDFs page in Web Courses After Class. And you'll be able to see how I put together those equations for a Ferrari driving off a cliff, as I mentioned in the textbook. Question?
Do you want the formula that it says for the parabola?
Yeah, what does it say? 1 over 4a times x squared.
It says y equals 1 over x squared, and that a is the distance from the vertex to the focal point of the parabola.
Yeah, so it's in the end of chapter 2. Y equals 1 over 4a x squared. And, you'll be able to figure out what a is equal to. And I believe that's actually one of the questions in the mini review, right? Number 7. It's a brain burner. Anyways, there's a talking PDF about it. And you'll be able to download that and listen to it sometime this afternoon. Now, I want to do a couple more clicker questions concerning first law. And there's a lot to the first law. We've just gone through 4 now, examples of it or concepts of it. Here's a clicker question for you. Multiple choice. This blue car moves to the right at constant speed. Which of the options, except for F, which you cannot vote for, all of the above, including none of the above. So you can't vote for F. But A through E, which one is? Read carefully. When you get to the exam on Tuesday, as I have said before, Read carefully and think.
By the way, all of the equations in the homework and then also here, they're going to be on the exam. Yeah?
The ones that you calculate with will be on the matching. The only exception is, and there may be some that you don't use, okay? The only exception is sometimes sometimes I can't put everything in matching that I want, so if you're going to need it, I'll put it in the question itself. For instance, as you know, the drop distance formula is d equals 1/2 gt squared. Therefore, which of these represents 2.5 seconds of free fall? And then A, B, C, and D. So I might do something like that, but most of them are going to be in the matching. So, all right, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Good. 196 of you guys voting. And most of you got it right. Constant velocity, yeah. Constant direction, constant speed. Now, I've got a little representation for it. What that means, in terms of a sketch, a diagram, a dot to represent the car, and then a red arrow to the right, and here's a sentence. And in this one, the equation V has a little arrow over the top of it, and you'll see me using that, that's vector notation. It means that I'm making a statement about something that has a direction, a vector quantity. All right, and the way that you would state it is, so much speed, 10.5 meters per second, comma, and then the direction that you're moving. All right, so in this case, it's VI equals 10.5 meters per second, for example, comma, rightward. Right. Now, if you got something that's, moving like this, like you throw a football and initially it's going up and to the right, then you'd have some horizontal and some vertical. So you'd have two components to specify. But this one's just to the right, so it's fairly easy. All right, next question. Can of Pepsi. Let's see if I can catch you guys napping here. Read carefully. Axel, are you here? Are you clicking? Good. $20 seconds. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, good. Let me show you the results here. It's a little bit of a contention there, a little bit of disagreement between B and C. B is correct, and there's more than one vertical force acting on it. All right, so one of the vertical forces is the weight force. So go ahead and make a sketch of a downward arrow. Now, this thing's at rest, right? So there's no unbalanced force. It remains at rest. It's not in free fall. So whatever this force is, and you're always going to have some weight force of some size, so there's always going to be a downward arrow. That means the table has to, wrong way. The table has to provide some upward force. All right, now that's the rigidity force of the table. The fancy word for that is the normal force, Normal. Which doesn't mean, well, it's just the same as everybody and everybody's normal and stuff. In physics and math, normal means perpendicular to the surface. So the surface is like this wall behind me, the normal would be out of it. And if you push into that force, into the wall behind me, the wall's going to push back normal to the wall, and that's going to be straight out horizontally. Okay? So normal force, and you know, you can't make a table out of liquid water. I mean, think about it, because liquid water doesn't have any rigidity. You can float something on it maybe. But like a can of Pepsi, no way. You know, you put a can of Pepsi onto a table made of liquid water, down she goes to the briny deep. All right? Now if you put a piece of paper onto a table made of water, yeah. But then, you know, but then eventually that'll go down to the bottom too. It'll get soaked and it'll start to sink. All right? So no delta V. So no acceleration. It's at rest, so no delta V. No acceleration. If there's no acceleration, there's no unbalanced forces. So we know one force is acting, that's the weight force. And we could write out, write out a vector description of this, but a little arrow is fine, this white arrow. And it's balanced by the rigidity force upward. And where does the rigidity force come from? Well, if you think about the tabletop made of plywood and plastic and some steel underneath that, it's like when you're on a trampoline. And if you've ever been on a trampoline, you know that if you get up onto the trampoline and then step out into the middle of it without trying to jump and do flips and stuff like that, you're just standing on it, you'll sink down, and you know the trampoline will go down like this into a shallow V, and then it'll stop and you'll be stable because the trampoline is kind of giving you some net upward force to balance your downward weight force. And the molecules and atoms in a solid, rigid surface will do the same. Now, if you put an elephant into a trampoline in your backyard, he'll demolish the trampoline. Same thing here. If you put an elephant up on top of this lectern, it'll demolish the lectern. So there's, eventually the trampoline will break. And that's how you break stuff. You exceed this trampoline strength. But a rigidity force, yeah, it's like, but you just can't see it because the molecules and atoms are so small. But that's what, and there's zillions of them. So every individual atom and molecule, and it's bonded to a neighbor, they don't dip down very much, but there's so many of them. The little bit that they do dip down is enough to support a can of Pepsi, or even this thing. Probably put 2 or 3 of you guys on top of it. And it wouldn't even groan. All right? Now, let's keep going. Newton's second law. What if you have something that's unbalanced? Well, if you have unbalanced forces, you're going to accelerate. You're not going to be in a state of constant velocity. Your velocity is going to change. So let's talk about that. All right? So what you do is you add up all your forces, and if anything doesn't balance, then the leftovers, whichever direction's got more force, that's the net force. That's the direction of the net force. So here's an example. We're going to, just take a hypothetical grab for the ball from the basketball, Dwight Howard versus LeBron James. All right, so now we're going to assume that Dwight Howard can put 100 units of force to the right. So he's got a bigger arrow than LeBron, and LeBron's got one to the left, but being a weenie that he is, I hope he never hears me say that. But anyways, let's just say that LeBron's only got 80 units of force, and notice that I put a minus sign on there to denote leftward direction. All right? So plus 100 plus a negative 80 is like 100 minus 80. The leftovers is 20 units of force to the right. And so you would write down a basketball or even a dot, and then a teeny tiny arrow to the right to represent the net force. All right, so that's the concept of net force. So with the apple in the apple tree, net force was 0. Can of Pepsi on the tabletop, net force was 0. But this one, LeBron versus Dwight Howard, the net force is to the right. Right? So they're going to accelerate. Right? And the more push or the more pull, the more acceleration. All right? So if you have LeBron versus his evil robot twin LeBron, then the evil robot twin LeBron might only have 81 units of force to the right, and so only 1 unit of net force. All right? He's still going to win the jump ball. I mean, it's not going to be a jump ball. He's going to grab it. But it's going to be a much tighter battle. Now, in this one, with Dwight Howard, 20 units of force, yeah, he's got it. No jump ball. All right? So the more push or pull, the more acceleration. But the more kilograms of mass you have, the less acceleration. So this is like saying, okay, take a little shrimpy first grader down to the supermarket and give him an empty shopping cart and then give him a full shopping cart that's totally loaded down. All right? Now that shrimpy little first grader probably be able to push the empty one down the aisle. But the fully loaded down, a lot of water and canned goods and stuff, totally loaded down shopping cart, he might not be able to budge it very well at all. All right? And that's because the shopping cart has more mass in it if it's loaded down, as I said. So here's the equation that expresses that. The more push, more acceleration means the push force, the net force, is going to be in the numerator somewhere, somehow. More kilograms of mass, less acceleration means kilograms of mass is going to be in the denominator. And this is the way it works out. The acceleration is equal to the quotient of the net force divided by the mass. Actually, this is how Sir Isaac Newton defined it. This defines net force. All right? A equals F net over M. Another way to write it, F net equals MA. Just cross multiply. All right, and this is the famous, so all engineering majors across the planet are constantly thinking about F equals MA. And if you happen to know an engineering major, you can always give him help. I'll help you with your homework. Just apply F equals MA. You'll never be wrong. And you'll astound your friend that's an engineering major. How did he know that? But it's true. F equals MA, it rules the cosmos, especially for engineers. Now, here's the set it over here on the right, 3 equations. The first one up there in the upper right, definition of acceleration. All right. A equals delta V over delta T. That's how we calculate an acceleration. We measure some distances, get some delta V's. Measure some distances and some times, get some delta V's. Then we make a ratio, delta V over delta T. We get an acceleration. Sir Isaac Newton said, second law, okay, we can measure that, and that's going to be the ratio between the net force with the mass. And F equals ma is just, saying the same thing. Now, I'm going to put the equation of the definition of acceleration in the upper right. I'm going to put that into the A of F equals ma. Right now, this is what, there it is, F equals m times the quantity delta V over delta T. That's kosher. All right, so, no funny stuff. I'm not trying to trick you. But if you do, so this is perfectly fine. And the nice thing about this is everything in there can be measured. So that is going to be very instructive for us. Here are the measurements. To get F equals m delta V over delta T, you got to have time measurements. You have to have a bunch of distance measurements. You got to keep them all organized. Plus, you got to measure the mass in kilograms. And we'll talk about that in a few minutes. How do you measure the mass essentially in kilograms in the metric system? And then you got to do some calculations. You got to do some velocities, get a delta V, and then from that you can get an acceleration, right? Now, what that tells you is something about the force acting. If you think of the interaction as a stopping interaction, so this is like if I'm in the grocery store and you're at the other end of the aisle, and I push a fully loaded cart at you, totally bench press it in your direction, it's going to be blazing down the aisle. And then you got to stop it, all right? And it's going to take you like a tenth of a second to stop it. But if you were a shrimpy little first grader, it might take 1 or 2 seconds. You need to be backing up the little first grader, okay? So if you're stopping something, in other words, figuring out stopping time, this equation tells you a lot about it because the stopping time is in the denominator, all right? So let's think about that. The stopping time if you have a stopping problem, or if you're operating in the Starship Enterprise, and you put a tractor beam on something and you bring it to a stop. The more stopping time you have, the bigger the denominator. So it doesn't require a large force. But if you have to have a really small stopping time, the denominator is smaller, and the way the denominators go, small denominator, big quotient. So you're going to have a larger force. All right, now that's just looking at this equation. But you know this from your experience working out. Right? You think about it, if you were up here on the stage and you jump down to the ground, or you're at the gym and you're doing a plyometric workout, box jumping. And you know that when you jump up onto the box or jump down from the box onto the ground for your workout, which is really good workout, you got to bend your knees. If you don't want, and if you don't bend your knees, if you land straight-legged, you're going to, be really sore. You're going to wreck your knees up if you keep doing it that way. Matter of fact, if you jump from a tall enough box and you land straight-kneed, you'll break your leg. All right? So longer stopping time means easier on your knees. Here's another one. And I'll just give this to you verbally. You're in a car traveling at 10 miles an hour. So you're on, and you're going to come to a stop not by applying the brakes, but by something stopping you. Now, let's say that you're in your car, it's going 10 miles an hour, so you're going to be stopped by something forcing you to stop. So let's go up north and think of a snowdrift. Now, snow is this white crystalline stuff, for those of you that are from Florida, that it comes out of the sky in the winter if you're up north, and forms big drifts and big piles. And if your car goes into a big pile of snow, it'll take a second or so to stop it. You'll stop, and then you're stuck. You're stuck in the snowdrift. All right? And that's because the snow does not give you a whole lot of force. The stopping time is pretty long. The stopping force is fairly small. And your car is stuck, but it's not wrecked. So if you get a toe out of the snowdrift, you're good. You can get back on your way. All right? And go skiing. Now, oppose that to another external object stopping you. Telephone pole. And you know, one of my first years here at UCF, I used to, in the afternoon, I would drive out along University, head west on University, and then, you know, and then branch off and head home, and because that's the direction I lived in. And I'll never forget it. This one idiot in front. There's so many bad drivers, you know, 3 or 4 in the afternoon. I'm sure no one in here drives like a maniac, but it does appear that there are a lot of maniacs on that stretch of road, and I'll never forget it. I'm at the light, right, and some guy in front of me goes through the light at the, you know, like the last second, so he's actually running the red light, a place I would never do, but I mean, anyway, so he's going through, and he must have seen somebody or seen something, because when I came out of the light, you know, like a minute and a half later or whatever it was, his car was in a telephone pole right over there by where Bar Louie is over there. All right, it used to be a telephone pole, and he must have seen something and veered off to the right, and bam, he went to a stop. He was out there scratching his head, and you know, what a mess. So you stop by a telephone pole. Telephone pole ain't going nowhere. Telephone pole offers you a whole lot of stopping force. And delta T, stopping time, is really, really small. And because because it ain't going anywhere, so you know your car's going to be wrecked. Huge stopping force, enough to crumple up the front of your car. All right? Unless you got like a Hummer. All right? I wish I had a Hummer sometimes. You just run, somebody's in front of you, just put it in low gear and drive over the top of them. But fortunately, they don't allow that in Florida. So now let's talk about measuring mass. Now, mass is the numeric quantity that carries inertia, or that, inertia, the measure of inertia of an object, the resistance to the change of dynamical state, is the mass. So the more mass you have, the harder it is to get you budged. So if you're in motion, it's hard to slow you down. If you're at rest, it's hard to get you going. Right? And if you're going in a certain direction, it's hard to change your direction. All right? You need a lot of oomph to do that. Now, in the metric system, the unit of mass is the kilogram. And basically, that's based on the gram, which is the mass of a cubic centimeter of liquid water, 27 degrees Celsius or something like that, in Paris. But that's what it's around. So basically, you take an object, you put it in the balance, and then you try to put some water on the other side of the balance. I mean, effectively, that's what you're doing. And then you're counting up the number of cc's of water that it takes you to balance. So like for this one here, okay, let's put a kilogram of water. That's a liter bottle of water over there on the left. And let's put wrong way. All right, so there's your kilogram of water. All right, now put a basketball on the other side. Now, a basketball doesn't have a full kilogram. All right, so if you do this, you put a kilogram of water over there, 1,000 cc's. Yeah, that's nice, but it's going to overbalance. So then you take out, 10 cc's of water, and you see, okay, is it balanced or not? Take out another 10, take out another 10. And you take out all the cc's that you need, and eventually you're going to balance it. And the number of cc's that you counted out that's left in the left side of the scale, that's the number of grams of mass in your object. Now, it's this business of counting grams of water is what they did when they invented the metric system. What they do now is they have metal weights. It's a lot less messy. And you go to Paris, you go to the museum, you see the international gram, international kilogram, international meter, all that stuff. All right, so they don't use water, but it's based on that. So somewhere somebody did use water. And they said, all right, this little chunk of metal here, that's 1 gram. And go ahead and make a note to yourself. A colloquial measure of mass, 1 gram, is a paperclip. A regular size paperclip. So not a jumbo one, not one of those big, ones that you could squeeze, but just a regular standard paperclip. It's about 1 gram. Okay, so here's some notes. 1,000 grams over on the left, and basketball is less than that. I think it's like 0.4 something kilograms, so not quite a full kilogram. Now, I'm going to ask you an F equals ma. We're still on second law here. F equals ma. You ready to do an F equals ma? Let's go. Multiple choice. Here's your question. You have a liter bottle of water, mass of 1.000 kilograms. It accelerates from so you pull on it, and you measure 1 meter per second squared of acceleration. What's the size of your net force? Just think, F equals ma. Fifteen seconds. 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Most of you got it right. 1.00 kilogram meter per second squared. A kilogram of mass times a meter per second squared of acceleration, that's what it is. All right, the other ones are not quite the right units. And hey, you guys, that quantity is the unit of force in the metric system. The nickname that we give it is the Newton, after Sir Isaac. And what you would say is a net force of 1 Newton accelerates a 1 kilogram object at the rate 1 meter per second squared. All right. Another thing I want to mention about this, meters, seconds, and kilograms we can measure. Kilograms, we can use a balance of some kind. Meters, we use a meter stick, tape measure, based on that bar in Paris, the international meter. Seconds are actually derived from the length of the day, the motion of the sun. So we can measure seconds. But newtons, we cannot measure. We must calculate a newton from basic measurements of mass, distance, and time. So we say that the newton is a derived unit. It's based on the basic units of distance, time, and mass. Another way to put it is you cannot go to Paris and go to some museum and look at, the international newton. In some little jar, covered by a glass jar. You can't do that. The meter, yeah. The kilogram, yeah. Second, not so much. I mean, it's based on you can see the sun moving every day, but you can't see the international meter. All right, let's try the force acting on not a 1 kilogram bottle of water, but a scary T-Rex, 342 kilograms. Okay, calculation time. Hit your refresh button. And let's do a numeric answer. Here it is. Calculate the weight force of a 342 kilogram T-Rex. And use the Earth's surface gravity, 9.8 meters per second squared. And we're just looking for a number of newtons. So don't worry about the direction. Don't worry about the minus sign here. Just calculate the weight force. And you don't really even have to worry about it because the weight force is always downward. So just the size of it is what we want here. Okay, and so type in the number that you get carefully. Consult with your neighbors and just double check your numbers. And remember to study for exam 1. It's really, really helpful, as some of my 9 o'clock students did. They banded together and they were studying yesterday. And hopefully you guys will do the same. And I see some of you didn't round off to the whole number. Don't give me a... All right, that's looking better, good. Some of you didn't round off properly. You're off by a single digit. Some of you are... I don't know what you're doing. $342 is not the answer. That's the mass of the T-Rex. $45 seconds. And don't forget to hit the send key when you're finished. $30 seconds. $15 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right. Raise your hand if you had 3352. Sweet. All right, so there's your answer. And a few of you typed in 3351.6. That's nice, but I asked you to round off to the nearest whole number of newtons. So you wouldn't get, if this were an exam question, you would not get full points. So you might get 2 out of 3, but you wouldn't get 3 out of 3. All right, so round off carefully. Now, I want to talk some more about the direction of the net force. Basically, this is the scoop. The net force on an object is equal to its mass times its acceleration. That's the F equals ma part. But the direction is going to point in the same direction as the acceleration. Right now, the acceleration you can measure. You can measure positions and times and figure out your acceleration. 1.5 meters per second squared to the right, or 2.7 meters per second to the left, minus 2.7 meters per second squared. All right, whatever it happens to be, you can measure that. And the net force, and that gives you the direction of the net force. So that's how you measure the direction. Remember, the force is derived and you derive it from the acceleration, the direction of it. Here's the vector equation that expresses that. F net with a little arrow over the top of it. All right, that when you see that arrow, that means I'm giving you a vector expression, meaning something that has a length and a direction, some direction. Mass times acceleration. In this equation, there's no direction for the mass. Mass is just a number of kilograms, a count, if you will, a count of cc's in the metric system, cc's of water. But acceleration, yeah, you can, it's going to have like north or up or, 45 degrees up and to the right or whatever direction it has. So you have to give that a little arrow over the top of it. Now, if the force can do three things, the net force anyways. It can speed something up if it's in the same direction as the motion. It can slow something down if it's in the opposite direction. So if your velocity is to the right and your net force is to the left, it's going to slow you down, at least to start. It can also change the direction. So if you're looking at a shopping cart at the grocery store going past you on the aisle, you're standing in the aisle and it goes past you down the aisle and you give it a bump, you bench press it, it'll change the direction from straight down the aisle and it'll plow to the other side of the aisle. All right? So the direction. Now, if you get a 45-degree angle force, a force that's 45 degrees away from your velocity, like this, like this Ferrari. So the Ferrari's going straight ahead, right? Okay. And so that little golden sphere is coming in at a 45-degree angle, right? So that thing is going to get a change in the speed and a change in the direction because it's coming in with a little bit of sideways velocity and a little bit of forward velocity. It's got a little bit of starboard. So this Ferrari is going to veer off to the right a little, veer off a little bit to starboard. And he's going to move a little bit faster. Maybe not that much, but theoretically he's going to move a little fraction of a mile an hour faster. Now, so that's kind of and we're going to get more into this in the next couple weeks. Let's talk about Newton's third law. This is a picture of Usain Bolt. And I'm going to burn your brains out in the homework this weekend with some third law questions. Now, if we had two skateboarders up here in the front, raise your hand if you got your skateboard today. Okay, Sawyer, you got yours? Yeah? Who else has got a skateboard? Nobody? Okay, you got one? Okay, who else has a skateboard? Okay, you've got one? Okay. All right, so those are three guys. Let's say that one of the ladies here had a skateboard. Now, they're usually going to be a little smaller than these burly guys in the back row. Okay? If they push off, if they're standing, which we did the first hour, if they push off, they're standing up here and they're facing each other and they do patty cake like this and then push off, they're both going to go in opposite directions. And the person who's lighter is going to go a lot farther. Okay? Now, here's an example of that from another textbook. An astronaut out in space, he gives a certain interaction force to a spacecraft to the right, and according to Sir Isaac Newton's law of action and reaction, for every action there's an equal but opposite reaction. the force of one object on another is equal but opposite direction to the force of the object on the first object. Okay, so the force of the spacecraft on the astronaut is to the left, same size. So whatever the skateboarders do up here in the front, and I'd call you guys up to the front, but we're running out of time. So whatever they have, 500 newtons of force, one guy's going to get 500 newtons positive, and the other guy's going to get 500 newtons negative. All right? Same as this one, the astronaut and the spacecraft. All right? But what they're not going to do is get identical speeds. Spacecraft is it's made of metal, so it's probably a lot heavier than the astronaut. All right? A lot more mass, a lot more kilograms. All right, now we're going to skip over this page, and what we're going to do is look at a textbook example from chapter 3, and actually what we're going to do is look at like the first 3 paragraphs of chapter 4.1, so make a note of that. Your exam is, we're going to actually dip our toes into chapter 4. So here's an example, 2 skateboarders, and I just kind of described it. So let's call them Carl and Bob. Here's the mass of Carl, and he's up here in the front of the lecture hall at rest. And here's his buddy Bob up in the front of the lecture hall. Double the mass, 80 kilograms. But also at rest, V subscript I equals 0. All right, so they're up here on the front, and they're doing patty cake, but they haven't pushed off yet. So let's add that in now. So now they push off, and their interaction force, according to Sir Isaac Newton, if their interaction is 500 newtons of push, that's fine. Then let's say that the force from Bob on Carl, okay, so Bob is pushing Carl to the right, 500 newtons. That means the force of Carl on Bob is minus 500 newtons. It's pushing them to the left. All right, so if we brought those guys down here, you'd see an example of it. Now, one thing about it, the amount of interaction time. So they're accelerating, right? They're interacting. And they're in contact for a certain amount of time. Now, let's say that the contact time is 0.48. Now, the definition of contact time, Carl's in contact with Bob for the exact same amount of time as Bob is in contact with Carl. So those two things are equal. The forces of interaction are equal but oppositely directed. The interaction time is equal by definition of contact. Now let's figure out their accelerations. We got the net force. We have their mass. We can figure this out. Carl, 500 newtons to the right, 40 kilograms of mass for Carl, 12.5 meters per second squared. A equals F over M. Ding. All right. Bob, a little bit different. He's going left. He's getting pushed over this way to the left. And so he's got a minus 500, and his denominator is 80 kilograms. All right, so he's dividing 80 kilograms out of there. So he's got a much pokier acceleration, but notice it still has that minus sign. He's gaining leftward. When you see an acceleration negative like that, that means you're gaining leftward leftward velocity. All right, let's do delta V. Carl, delta V, 12.5 times 0.48, easy peasy, 6.00 meters per second. Bob, little bit trickier, has got a minus sign, but not too bad, negative 3.00 meters per second. And notice that Carl is smaller, he gets more speed. So the final velocity states, their initial velocity states were both 0. So whatever they get in the delta V, that's their final velocity state. Positive 6 for Carl, minus 3 for Bob. Now, what we're going to talk about and what we're going to kind of jam forward here, I want you to emphasize the interaction force. It's going to be plus or minus 500. And the interaction time, delta t. So this is not a stopping time, but you would call it an interaction time. 0.48. Those are the things that are equal for both of them. Now we're going to skip over this. We're going to skip over this. And here is what we call the impulse equation. The interaction force is the same for both. The interaction time delta t is the same for both. The only difference is the F's are plus or minus. And that means the quantity m delta v, as you'll read about in the textbook, this is actually the first couple paragraphs for chapter 4.1, m delta v is going to be the same but opposite direction for both. So the size is going to be the same. And look at that. We know that that's the case. Bob and Carl have different masses, and they also have different delta V's. But the product is the same for both of those guys. And we'll dismiss in just a second. Sir Isaac Newton, this is the way that he thought about the interactions. He thought in terms of impulse, F delta T, and the change in this quantity, mv. Now, next week we're going to use that equation to tackle stopping time problems. For now, listen carefully. Here's what we've got for coverage. We got 3.7 in the first 3 paragraphs of chapter 4.1. All right, so just a little bit there. But we skipped over 3.6 about uniform. We'll take care of that next week. Uniform circular motion. And we skipped over all of 3.8, 3.9, 3.10 about universal gravitation. We'll tackle that next week. All right? So from introduction of 3.7, except for 3.6, we'll leave that for next week, and just a little nibble at the very front of chapter 4.1, first 2 or 3 paragraphs, okay? So there's your coverage. See you on Tuesday. You're dismissed.